In this video, we will be looking at some of the predictions that Lewis dot structure theory makes regarding bond length and bond strength and how these play out in actual structures. Lewis theory predicts that the more electrons two atoms share, the stronger the bond will be, meaning that a single bond is weaker than a double bond, which is weaker than a triple bond. Or put another way, triple bonds are stronger than double bonds, which are stronger than single bonds. This is consistent with the bond energies that we saw in our previous video. Lewis theory would predict that double bonds are twice as strong as single bonds, but in reality, they are stronger but not twice as strong. Bond strength themselves must be measured by the amount of energy that is added to break the bond in half. Lewis theory also predicts that the more electrons two atoms share, the shorter the bond will be. This is when comparing bonds with similar atom types. So a carbon-nitrogen single bond versus a carbon-nitrogen double bond. The prediction is that the carbon-nitrogen double bond, which shares more electrons in the bonds, will be shorter than the carbon-nitrogen single bond. The bond length is determined by measuring the distance between the nuclei of bonded atoms. So for example, the bond length for a fluorine single bond would be 143 picometers. For a chlorine single bond, it would be 199 picometers. In general, triple bonds are found to be shorter than double bonds, and double bonds are found to be shorter than single bonds. As we move down the periodic table, you will also note that because the atomic radii increases, the bonds that involve larger and larger atoms will have larger and larger distances. Again, it is the distance between nuclei of the bonded atoms that is called the bond length. Because the actual bond length depends on other atoms that are around the bond, similar to how the bond energies depended on what was around the bond, we often use average bond lengths when we're putting them into tabular form. The average bonds themselves come from similar compounds. So, for example, a carbon-hydrogen bond, there are many different compounds that have carbon-hydrogen bonds. The average bond length for a carbon-hydrogen bond is 110 picometers. As we look down the column here, we notice that, for example, the fluorine, chlorine, bromine, iodine, as we're moving down the periodic table, the atom that the hydrogen is bound to is getting bigger, and thus the bond length is also getting bigger. That's because one of the things that dictates the bond length is the size of the atoms involved in the bonding. So also, as we go across the periodic table, if we're looking at carbon, nitrogen, oxygen, and fluorine, this is moving across the second row, we note that a hydrogen-carbon bond is longer than a hydrogen-nitrogen, which is longer than a hydrogen-oxygen, which is longer than a hydrogen-fluorine. Part of the reason for this is that the fluorine atom is smaller than the oxygen atom, which is smaller than nitrogen, which is smaller than carbon. One of the key components that makes up our bond length is the size of the atoms involved in the bonding. So if we keep one of them constant and vary the other, we can get a general idea of the trend that we expect in our chemical bonds. Also, when we look at bond lengths, as we increase the order of the bond, so going from a single bond to a double bond to a triple bond, we note that the bond length contracts. So a triple bond is shorter than a double bond, which is shorter than a single bond. But note that a double bond is not half the distance that a single bond is. It's just smaller. So some of the general trends that we can say about our bonds are, in general, the more electrons two atoms share, the shorter the covalent bond will be. In making that comparison, however, you need to be comparing similar atoms. So that would be comparing the bond lengths of a carbon-carbon triple bond to a carbon-carbon double bond to a carbon-carbon single bond. It's not quite fair to do a comparison of a carbon-carbon bond to a carbon-nitrogen bond. Also, generally, bond length decreases from left to right across the periodic table. And this is again because one of the key components that makes up the bond length are the radii of the atoms involved in the bonding. So a carbon-carbon single bond is longer than a carbon-nitrogen bond, partially because the carbon atom here has a larger atomic radii than the nitrogen does. And the carbon-nitrogen bond is longer than a carbon-oxygen bond for a similar reason. Also, generally as we go down the periodic table or down a column, the bond length increases. This again is because the atomic radii of the atoms involved in the bond increase, making the bond length longer. In general, as the bond gets longer, they also get weaker. We can see this by comparing bond lengths to bond strengths.